Training a large language model typically consumes 16 bytes of memory per parameter, 4 for the weights, 4 for gradients, and 8 more for optimizer state. That overhead means a model with 8 billion parameters demands over 100 gigabytes just to update its weights, locking out researchers without industrial-scale hardware. FlashOptim attacks this problem at the optimizer level. Instead of storing 32-bit master weights, it splits each weight into a 16-bit downcast and an 8-bit error correction field, exploiting the non-overlapping structure of rounding errors. Optimizer states like momentum and variance are compressed to 8 bits using companding, non-linear functions that reshape value distributions before quantization to prevent catastrophic information loss. Let's examine how the weight splitting mechanism actually works. The splitting strategy leverages a mathematical property. When you round a 32-bit float down to 16 bits, the error's exponent never overlaps with the result. That means the correction lives in a narrow numerical band, 1 unit in the last place, which fits cleanly into 8 bits. This achieves bitwise reconstruction for 99.9% of all 32-bit values, with dramatically lower relative error than prior methods, particularly where precision matters most, at small magnitudes. The second pillar is how optimizer states themselves are compressed. Momentum and variance buffers have wildly non-uniform distributions. Variance especially suffers from extreme outliers. If you quantize them linearly to 8 bits, training collapses immediately. Companding solves this by warping the value space first, soft sign for momentum, square root for variance. These mappings spread out the bins where values actually cluster, cutting normalized error by more than an order of magnitude and rescuing training from divergence. On a real workload, fine-tuning Llama 3.1 with 8 billion parameters, FlashOptim cuts peak memory from 175 gigabytes down to 113, a 36% reduction. Per parameter memory drops from 16 bytes to 7, or even 5 with aggressive gradient release. Checkpoints shrink by half. Optimizer state alone loses more than 60% of its footprint. Despite having memory, model quality stays intact. Loss curves for GPT-2 pre-training, ResNet 50 on ImageNet, and Llama fine-tuning are indistinguishable from full precision baselines. This holds across SGD, AtomW, and Lion optimizers. Convergence speed doesn't change. Validation accuracy doesn't drop. The transformations are semantically transparent. FlashOptim shines on parameter-heavy architectures like transformers, where optimizer state dominates memory. For activation-heavy models, think high-resolution vision networks, the overall gain is modest unless you also checkpoint activations. Some edge cases in specific domains may still need selective fallback to higher precision, but the framework supports per-layer exclusions. FlashOptim proves you can compress every component of the training loop, weights, optimizer state, even checkpoints, without touching convergence or accuracy, as long as you respect the structure of numerical error. That opens the door to training billion-parameter models on hardware that was previously too small. Visit emergentmind.com to learn more and create your own research videos.